Hi, everybody. My name is Rongpu Zhou. I'm a postdoc at the Berkeley Lab, and I'm also a member of the DESI collaboration. Here, I'm going to give you an overview of the DESI project. The primary goal of DESI is to measure the expansion history of the universe and the dark energy equation of state. And to achieve this goal, DESI will measure the redshifts of millions of galaxies and quasars, and in the process, create a 3D map of the universe. The top figure here shows the number of galaxies observed by spectroscopic surveys over time, and DESI will continue this trend with an order of magnitude increase in the number of galaxies compared to previous surveys. The bottom figure illustrates how well we expect to measure the expansion rate as a function of redshift with DESI. Besides dark energy, DESI will also measure the growth of structure and enable tests on models of modified gravity. It will measure the sum of neutrino masses and also the power spectrum from primordial fluctuations. Enabling these measurements are some remarkable instruments at the Mayo 4-meter telescope at Cape Peak. This includes the 6-lens optical corrector, including atmospheric dispersion corrector elements. They enable an extraordinary 8-square degree field of view. There are 5,000 robotic fiber positioners, and the top right figure shows the fully populated DESI focal plane, where each tiny spot is a fiber positioner. The 5,000 fibers are then fed to 10 spectrographs, each with 3 arms, shown in the bottom figure. They cover a wavelength range between 3,600 and 9,800 angstrom, and they have high enough resolution to resolve the O2 doublets at this entire wavelength range. The DESI survey will be conducted over a span of 5 years, covering an area of about 14,000 square degrees. There are 4 target classes in the DESI redshift survey. At the highest redshift are the quasars. Below redshift 2.1, the quasars will be used directly as tracers of matter. And above redshift 2.1, they'll be used for Lyman alpha for its measurements. Between redshift 0.6 and 1.6 are the emission galaxies, which are star-forming galaxies with strong O2 emissions that allow for secure redshift measurements. At redshift 0.3 to 1 are the luminous red galaxies. These are massive galaxies that have long-lived star formation and are similar to the LRG samples in SDSS. At the lowest redshift is the bright galaxy survey. It is a magnitude-limited survey similar to the Sloan main galaxy sample, but it's much fainter. In addition to the redshift surveys, DESI will also measure or perform a Milky Way survey, which will measure the radial velocities and metallicities of about 10 million stars. Before we can perform spectroscopic observations, we need to know where the spectroscopic targets are on the sky. The selection of DESI targets require imaging that is both wide enough to cover the entire DESI footprint and also deep enough and uniform enough for accurate photometry of the targets. The imaging data for DESI comes from 3 imaging surveys, DECALS, BAS, and MZLS, and they are collectively called the DESI Legacy Imaging Surveys. There are 3 optical bands, GRZ, and we also borrow a little bit of imaging data from the dark energy survey. The figure here shows the imaging footprint, and I've also included a red dashed line to show where roughly the luminal declination limit is for DESI. Here I've also listed the depth of DESI imaging and SDSS imaging for comparison. And as you can see, DESI imaging is much deeper than Sloan. Besides the optical photometry, we also include infrared force photometry from the WISE satellite, and it plays an important role in the LRG and quasar target selection. All this imaging data are processed by the DESI imaging pipeline, and we use an algorithm called Tractor that performs for modeling multi-band, multi-epoch source extraction. All this imaging data and source catalogs are public, and you can find the latest data release at this URL. In October last year, DESI achieved a spectroscopic first light, and since then it has completed the commissioning phase and has been approved for CD4. In other words, it is the first stage for dark energy experiment to go on sky, and we are all super excited. The figure on the right shows that DESI has been rapidly collecting spectra before the COVID shutdown. And the left figure shows a beautiful spectra of a post-starburst galaxy at redshift 1.3 taken during commissioning. As soon as DESI goes back to normal operation, it will start the survey validation phase, during which we will optimize the target selection and spectroscopic pipelines. As a wide-field spectroscopic survey, DESI is highly complementary to large imaging surveys such as Rubin. Here I will very briefly highlight some of the synergies with Rubin, and of course this is by no means an exhaustive list. First, uncertainties in the photo-Z ratio distributions will be a major source of systematic uncertainty in the weak lens in cosmological analysis. And DESI redshift would enable calibration of the redshift distributions using the cross-correlation technique. DESI redshifts will also benefit supernova cosmology. And this is because a significant number of supernova host galaxies in the overlapping footprint will already have spectroscopic redshifts from the DESI BGS and NRG samples. DESI redshifts will also enable galaxy-galaxy lensing using spectroscopic lenses, and combined with precise three-dimensional galaxy cluster measurements, they will provide an important cross-check to the cosmic shield results from Rubin. There is also benefit to studies of intrinsic alignment. Precise redshifts from DESI breaks the degeneracy between intrinsic alignment parameters and photo-Z uncertainties, and they provide greater constraints on intrinsic alignment models than could photometric data alone. And finally, besides the immediate 5-year DESI survey, we should also start thinking about the opportunities after the 5 years of DESI, when we can use the northern part of the Rubin imaging for targeting on DESI. Now, I would like to thank all our sponsors, and thank you for your attention.